So when we were looking at the magnetic field, or what the compass was doing, we had our current carrying wire taped down to the page, and let's just say, for instance, the current was directed to the right, and so this is just the rest of the wire out here and out here. Okay, so the current was going to the right, and we had put red thread in the shed or something like that, and we had our original compass needle pointing to the right, but we connected the circuit, and we saw that the compass needle did this little deflection. So we saw the compass needle deflect by an angle, some angle theta. We could have measured it, and some of you did. Now, if we say that the magnetic field and the variable used for magnetic field is the letter B, as in boy, as not in magnetic fields, if it's proportional to or can be determined by the angle of the deflection, then we could say the magnetic field strength is directly related to or directly proportional to the angle of deflection. Now, as we picked up that compass and pulled it away from the wire, we saw that the deflection angle was decreasing. So, if we were to create a graph of the electric field strength, and I'm going to use the B as related to R, we would see it trail off like this. And that means that our magnetic field must be proportional to the inverse of R. Now, what do you think would happen if we add more current? So instead of one current carrying wire to the right, or one I, we added another current and another current and another current, or increased the current. Maybe this current is 10 times what we had to begin with. Now, do you expect that the compass needle would be deflected the same or more? It's more. There's more current that is creating a magnetic field there. So if we were to graph the relationship between the magnetic field strength and the current, we would see a nice direct relationship telling us the magnetic field is directly proportional to the current. Putting this together, we could write that our magnetic field strength of a wire depends on the current and is indirectly dependent on the distance of separation. Now, if you watched in the video of the magnetic field around the wires, we saw that a current carrying wire creates a magnetic field that runs in circles around the wire. So pretend that these are pretty concentric circles. And if I stick my thumb in the direction of the current and grab the wire, I would have a magnetic field that was directed down in front, and tangent here, and tangent there, and up in the back, and across in the... Now, because of the circular nature of the magnetic field around the wire, where R is the distance from the wire to the the place that we're looking at. The magnetic field goes through that place. We get this 2 pi in the denominator, and then we have a constant mu naught that represents the permeability of free space, which has a value of 4 pi times 10 to the negative 7. So, our current is measured in amps. Our distance is measured in meters. And the magnetic field is measured in Tesla for Nikola Tesla. So the unit for our permeability of free space, of free space ends up being 4 pi times 10 to the negative 7, and it would be in Tesla meters per amp.